In this video, we're going to continue looking at lines and planes in space, and now we're going to look at the distance between points, planes, and lines. And specifically, we're going to look at between points and planes and points and lines, because if you're given two planes or two lines, all you really need to do is pick your favorite plane or line and find one point on them, and then you're back to the same situation between points in a plane and points and lines. So we're going to look at, in this video, finding the distance between a point in a plane and a point in a line. That distance is going to be between the point Q and the plane. So you'll have a plane with point P on it and Q somewhere off of it. And we're looking for the shortest distance from P to Q. And of course, our normal vector will be involved. Our formula for our distance is going to be the absolute value of the dot product of PQ dotted with n divided by the magnitude of n. Again, P is a point on the plane, n is the normal vector to the plane. And to find a point on the plane, we'll let y and z be 0, and then we'll find the x that keeps our statement true. And if we're looking at the example ax plus by plus cz plus d, if y and z were gone, I get ax plus d equal to 0. So then x has to be a negative d over a. That would be the x value of the coordinate, and then y and z would be 0. That point would lie on the plane, and then you can take that point P and figure out how to get to Q. So let's find the distance between point Q, 1, 5, negative 4, that's the one off the plane, and from the given plane 3x minus y plus 2z plus equal to 6. Finding a point on the plane will be relatively easy. I'll let y and z be 0, and so x has to be 2. 2, 0, 0 is a point on the plane. You can use different points. This is just the one I'm going to use. Now the normal vector I don't think is quite as obvious when you see the solution. It says you know that, of course, the normal vector is 3, negative 1, 2, and that is to the given plane. And it's maybe not so obvious until you look at the video that I have linked here to Khan Academy, or you can go back and look at slide 15. Because what happens is, if you have the equation of the plane, you can then begin to work backwards to pull out this A, B, and C. And what you'll see is that the A, B, and C here in front of the X, Y, and Z will have to be the same in the normal vector. This D value comes from whatever point you pick along that plane. And so the vector, the normal vector to the plane, will be the same A, B, C value from the equation. But you can look at the proof in this lovely video at Khan Academy, or you can go back and check out slide 15. So we got our normal vector, we have our point, we're ready to find some dot products. PQ is going to be easy enough to be found using our position vector, so 1 minus a negative 2, 5 minus 0, negative 4 minus 0, and there's my vector PQ. We're going to dot that with n, and then we're going to find the magnitude of n underneath. And so I'll have a negative 3 plus a negative 5 plus a negative 8. I'll get a negative 16. Of course, I want the absolute value since we're talking about distance. And I have 16 over the square root of 14, and that's my distance. So all the work is actually in the before you can even get to the distance formula. That's from a point to a plane. If you were looking between two planes, you would pick one plane, find a point on it, and then use that as the Q value. If I want to find between a point and a line, it will be a little bit more involved because I don't have the normal vector. We're going to need to go ahead and find that. And then find that magnitude. And so I'm looking for the PQ crossed with U, which is going to be our line, the magnitude of that normal vector, and then the magnitude of just U. And we're going to have to go over to WebDesign to do an example. Our example is find the distance between the point and the line given by the set of parametric equations around 3 decimal places. Let's bring over our formula to remind us what we are looking for. And then actually it's very nice that they gave me the parametrics, because now I don't have to work very hard to find the normal vector, a point on the line. So my vector can be built from my direction numbers. So u has to be 2, 1, 2. And of course a point along that line, so this is how I was moving, so that's my direction. And then I was starting, remember, at the constants, and that's going to be P, that's a point on the line, which would be 0 since there's no constant in the x expression, -3 and 2. I want the distance to Q, so that has to be Q. So I can find PQ, which has got to be Q minus P. So I have 3 minus 0, -7 minus a -3, and 7 minus 2. And there is my vector PQ. So now I have PQ, and I got U, I have U, and so let's go ahead and cross the 2. And I have I, J, K, PQ, and U. My coefficient for I would be 8, -8 minus a 5, which is going to be a -13. I'm going to negate the coefficient of the J, which would be 6 minus a 10. 6 minus 10 is a -4. Keep the sign on the last determinant, which would be 3 minus a -8, so plus an 8. How about an 11? And so my normal vector is -13. Where am I? 4, 11. That's n. And I can find the magnitude of n. So I have 169 plus 16 plus 11 and I will get, oh, how about 121, not 11, 11 squared plus 16, and I get the square root of 306. That's my numerator, and my denominator is the magnitude of u, which was 212. Yeah, so I have 4 plus 1 plus 4, known as 9. Well, that's nice, so 3. So how about all of that for a distance of a radical 306 over 3? If I remember correctly, they said to round 3 decimal places. And how about 5.831? That is about my distance, 5.831. And that's how you find the distance between a point and a plane, and a point and a line.